In this video, we are going to discuss the three methods of energy transfer. The first one is going to be conduction. Conduction occurs through an exchange of kinetic energy due to collisions. So imagine that you have a pot of boiling water and you put a metal spoon in the boiling water. Now what's going to happen is that the particles that make up the spoon that are actually in the water are going to start moving around a lot more, and they're all going to collide into each other. And eventually the particles here are going to collide with the particles that make up this section here, which are then going to collide with the particles that make up this section, and then it's going to keep going and going and going and going until all the particles have a little bit more kinetic energy due to collisions from the particles next to them. That means even though the initial energy came from down in here, it's now been transferred up here, and so when you go to grab the spoon, the handle is hot, which is why you tend not to use metal spoons for cookware, especially when you're stirring a hot pot. You tend to use plastic, and plastic is more of an insulator. It doesn't allow energy to transfer as much. Keep in mind, an insulator does not allow for the easy transfer of energy, and a conductor does allow for the easy transfer of energy. The difference between the two tends to be the amount of free electrons that you have, because remember, you need those electrons to collide with each other in order to transfer the kinetic energy. Metals, which tend to be bigger atoms, have more free electrons because the distance between the outer electrons and the positively charged nucleus is pretty big. So that positively charged nucleus cannot hold on to the electrons as well, so they have more of an ability to escape and move around a little bit inside the metal. Now let's talk about how we're going to calculate the rate at which energy is transferred. Remember, the rate at which energy is transferred is power. And remember, power is energy per unit time. So we're going to be talking about the rate at which this energy is transferred. And we're going to calculate that specifically for conduction using a lowercase k, and the lowercase k stands for the thermal conductivity. And thermal conductivity is going to be given in joules per second meters degrees Celsius. And this value depends upon the material that the energy is flowing through. So something like a metal is going to have a fairly high thermal conductivity because it easily allows the transfer of energy, but an insulator, so something like plastic, would have a much lower thermal conductivity because it acts as an insulator and does not allow for as much conduction. The next thing we're going to multiply by is the area through which the energy is flowing. So if we talk about a window pane, it would be the area of the window pane. This is then multiplied by the difference in temperature. So we're going to do temperature hot minus temperature cold. Because we're subtracting, we could use either Celsius or Kelvin, but both temperatures must be in the same temperature units. And then we're going to divide by L, where L is the distance the energy travels. So once again, if we talk about the window, it would be the thickness of the window pane. Because this is power, we're going to end up with units of watts. The next way we are going to transfer energy is convection. Now when we talk about convection, we are once again talking about moving material around, but when we talked about conduction, it was those electrons just moving a little bit, colliding, and then moving back somewhere else. Here we're actually going to talk about the mass motion of a substance. So we're going to have a heat source, and it's going to heat up a gas above it. And as the temperature increases, the substance expands and the density goes down. This is going to allow the substance to rise. Because remember, less dense items float. It's going to rise to a point where it can give off its energy. This is going to cause the temperature to go down, the volume to go down, and therefore the density to go back up, and it sinks again, because the more dense item will sink. We aren't going to get into the complexities of where exactly it gives its energy off. We have plenty of other courses that allow you to work with convection within the Earth's atmosphere, like an earth science or meteorology course. So examples of this is actually everywhere. So we get this transfer of energy through the mass motion of material. It occurs underneath the Earth's surface, is what drives plate tectonics. So this is occurring inside of the mantle of the Earth. This is what drives a lot of our different climates, where the air rises at the equator full of moisture, it rains over the tropics, and then comes back down through the desert with all of its water now gone, which is why it's dry in the desert. It occurs inside the center of the sun. So convection is everywhere. It's also why a lot of times the ceiling in your house is a lot harder than the floor that you're actually standing on. So this is why my cat loved my brother's bunk bed when I was a kid, because he would sleep on the top bunk where all the hot air had risen to. The last method of energy transfer we're going to talk about is radiation. Radiation is the transfer of energy through electromagnetic waves, which is a very technical term for light. So this is why you can stand next to a fire and be warm without actually having to touch the fire, because infrared radiation is coming off of the fire. This is the same thing that happens with, if you've ever watched a cop show when they're using the infrared guns in order to see somebody's body heat through a wall. They're picking up on the infrared radiation or light that is coming through the wall. We are going to calculate the energy transfer, so the rate at which energy is transferred, a slightly different way than we did for conduction. So once again, the rate at which energy is transferred is power, and this is going to depend upon a couple of different constant values. The symbol here, this is a lowercase sigma. I have a hard time writing lowercase sigmas. They always end up looking like sixes. And the sigma is going to be the Stefan Boltzmann constant, different than the Boltzmann constant. And it's going to equal 5.6696 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Let me make that 9 a little clearer in here. The next term is going to be the area, and this area is going to be the surface area through which the energy is going to flow. The next term here, this lowercase e stands for emissivity. And this tells you how good of an absorber or radiator the object is. So an emissivity of 0.6 would tell you that it radiates 60% of its energy. An emissivity of 0.3 tells you that it radiates 30% of its energy. Now there's a special type of object called a black body, and it's going to have an emissivity of 1, where it absorbs and re-emits all the energy. So it's sort of an ideal scenario. And we tend to model stars as black bodies. So if I give you a problem with a star in it, you know the emissivity is 1. Our last term in here is temperature to the 4th power. And this temperature must be in Kelvin, because we're not doing a delta T, we're doing a T to the 4th power. Another thing we can do with this relationship is compare the rate at which the object is going to either absorb or emit energy compared to the surroundings. So we would have all the same variables out front, but then we would do a difference in temperature. And these still have to be in Kelvin because they're raised to the 4th power. And this here would be the temperature of the surrounding. Another thing that you can do with this formula, and let me bring up another sheet because I've run out of room, is very similar to what you did with the ideal gas law, where if you have two objects, so let's say we do object 2, and we can compare it to object 1. So you can determine how much more surface area something has compared to another star given certain conditions. You can figure out the amount of power one star has compared to another by utilizing the ratio of the radiation equation for power.